Hello, my name is Sandya Prakash. My roll number is 2095182170 from Aeronautical Engineering second year section B. Today's my topic is demonstrate R trees from data structures. Uh, R tree is a tree data structure used for storing spatial data indexes in an efficient manner. Our trees are highly useful for spatial data queries and storage. Some of the real-life applications are mentioned below that are indexing multi-dimensional information, handling geospatial coordinates, implementation of virtual maps, and last one is handling game data. These are some pictures of our trees. Coming to the properties of arteries, consist of a single root, internals, nodes, and leaf nodes. Root contains the pointer to the largest region in the spatial domain. Parent nodes contains pointers to their child nodes, where region of child nodes completely overlaps the region of parent nodes. Leaf nodes contains data about the MBR to the current object. MBR minimum bounding regions refers to the minimal bounding boxes, the parameters surrounding the region or object under the consideration taking through it. Right? Comparison with quad trees, tiling level optimization is required in quad trees, whereas in R trees doesn't require any such optimization like quad trees. Quad trees can be implemented on top of existing B trees, whereas R tree follow a different structure from a B tree. Spatial indexes creation in quad tree is faster as compared to R trees. R trees are faster than quad trees for nearest neighbor queries, while the Windows queries quad trees are faster than R trees. This is a comparison between the quad trees and the R trees. R trees are tree data structures used in spatial access methods for indexing multidimensional information such as geographical coordinates, rectangles, or polygons. The R trace was proposed by Antonin Goodman in 1984 and has found significant use in both theoretical and applied contexts. A common real-world usage for an R trace might be to store spatial objects such as restaurant locations on the polygons. That typical maps are made of streets, buildings, outlines of lakes, coastlines, and etc. And then find answers quickly to queries such as find all museums within 2 kilometers of my current location, leaving retrieve all loads retrieve all load segments within 2 kilometers of my location to display them in a navigation system or find the nearest gas station. Although not taking the roads into account, arteries can also accelerate nearest neighbor search for various distance metrics including great circle distances. The key idea of the data structure is a group nearby object and represent them with their minimum bounding rectangles in the next higher level of the tree. R. An R tree is for rectangles since all objects lie within these bounding rectangles. A query that does not intersect the bounding rectangle also cannot intersect any of the contained objects at least leaf level which rectangle describes a single object at higher levels, and aggregation includes an increasing number of objects. This can also be seen as increasing common approximation of the datasets. Data layout. Data in R trees is organized in pages that can have a variable number of entries up some predefined maximum and usual above a minimum fill. Each entry within a non-leaf node stores two pieces of data, a way of identifying a child node and the boundary boxes of all entries within these node. Leaf mode stores the data required for each child, often a pointer or bounding box representing the child and an external identifier for the child. For point data, the leaf entries can be just the points themselves. For polygon data, that often requires the storage of large polygons, the common setup is to store only MBR, minimum bounding rectangle of the polygon, along with a unique identifier in the trees. In range of search, the input is the search rectangle query box. Searching is a quite similar to searching in a B plus tree. Search starts from the root node of the tree. Every internal node contains a set of rectangles and pointers to the corresponding child nodes, and very leaf node contains the rectangle of spectacle objects. For every rectangle in a road, it has to be decided overlaps the search rectangle or not. If the corresponding child node has to be searched also, searching is done like this is a recursive manner until all overlapping nodes have been transferred. When a leaf node is searched, the content bounding boxes rectangles are tested against the search rectangle, and their objects are put into the result set if they lie within the rectangular. Insertion. To insert an object, the tree is transferred recursively from the root node. At each step, all rectangles in the current directory node are examined, and a candidate is chosen using a heuristic such as choosing the rectangular which requires least enlargement. The search then descends into the space until reaching a leaf node. If the leaf node is full, it must be split before the insertion is made. Again, since an exhaustive search is too expensive, a heuristic is employed to split the node into the two. Adding the newly created node to the previous level, this level can be again overflow, and these overflows can propagate up to the root node. When these node also overflows, a new root node is created and the tree has increased in height. Choosing the insertions in subtrees. Uh, The algorithm needs to decide in which subtrees to insert when a data object is fully contained. A single rectangular choice is cleared when there are multiple options or rectangles in need of enlargement. The choice can have a significant impact of the performance of the tree. The objects are inserted into the subtree that needs the least enlargement. A mixture heuristic is employed throughout. What happens next is it tries to minimize the overlap. Uh, at the higher levels, it behaves similar to the R trees, but on ties again preferring the subtree with smaller area that decreases overlap of reflecting in the R tree is one of the key benefits over the traditional R trees. Splitting and overflowing node. Finally, the X tree can be seen as R tree variant that can also decide Do not split a node, but construct a so-called super node containing all the extra entries when it doesn't find a foot split, in particular for high dimensional data. Deletion. Deleting an entry from a page may require updating the bounding rectangles of parent pages. However, when a page is wonderful, it will not be balanced with neighbors. Instead, the page will be dissolved and all its children, which may be subtrees, not only leaf subjects, will be reinserted. If during this process the root node has a single element, the height can be bulk loading. Nearest X objects are sorted by their first coordinate X and then split into the pages of the desired sizes. Packed hybrid are trace variation nearest X, but sorting using the Hilbert value of the center of the rectangle instead of using the x coordinate. There are no guarantees the pages will not overlap. This is about my topic, and thank you so much.